Hello, dear colleagues. In this discussion, we are going to be looking at half-life in chemical kinetics. So, in chemical kinetics, half-life, or T a half, is the time required for half of the reactant in a chemical reaction to be consumed or reduced to its half at the initial concentration. So, if we have an initial concentration of a reactant being, for example, if we take A, if its initial concentration is concentration of A naught, that is at T is equal to 0, if we say it is going to reduce to a particular amount after a time equivalent to its half-life, then after T a half, this amount is going to be reducing to concentration of A divided by 2. So that's what we are meaning. The time required for half of the reactant in a chemical reaction to be consumed or reduced its half the initial concentration. It is therefore an important concept for understanding how quickly reactions proceed. So the key important points about half-life include, we have already said that it is the time during which the concentration of reactant decreases 50% of its initial value. So we have said if we have the concentration of A after half-life, that is after T a half, the concentration of A will be the concentration at time is equal to 0 divided by 2. So this is the concentration of the reactant at time T, and this is the concentration of the reactant at time is equal to 0. So this half-life depends on the order, and the half-life varies based on the order, therefore, of the reaction. So for zero-order reactions, the half-life depends on the initial concentration. For the first-order reactions, the half-life is a constant and is independent of the initial concentration. Then for second-order reactions, the half-life depends on the inverse of the initial concentration. We are going to be seeing at the formulae so that you can be able to differentiate between the half-life for zero-order, first-order, and second-order reactions. So the applications of half-life, we shall see that why do we need to study half-life? So half-life is studied in order to determine the age of fossils or artifacts, and that is an application of radioactive decay. So also there is another application in drug kinetics. So half-life helps in calculating dosage and intervals in medicine. Another application is also that in environmental chemistry, we use half-life to determine the persistence of pollutants or insects or pesticides. For example, if we have some pesticides or pollutants that could be persisting in the environment, so we need to determine from the very initial concentration. So from the initial concentration, after some particular time, okay, we'll be able to also determine the concentration there. So half-life, having a hint about the half-life of that pollutant, will be able to determine how long that pollutant is going to be in the environment, and therefore we devise means of avoiding it or managing the effects. The reaction monitoring, we see that also a half-life assessing the progress of a reaction. If we are able to determine how long the concentration of reactant is going to be reducing to half of its initial concentration, then we can be able to tell the progress. If the half-life is longer, then we can say maybe the reaction is very slow. If it is, if we have a very short period of time, then the reaction is very fast. So understanding half-life, therefore, it provides insights into the speed of reactions and their practical implications in various fields. Now let us look at the formulas for rate equations and half-life in different reaction orders. So our first to deal with is the zero order reactions, which is a very simple and basic case. So we find that its half-life is half of the initial concentration divided by K. So K is the rate constant, and we can see that the half-life decreases as the initial concentration decreases. Now we are going to look at the formulae for how do we generate this equation, and also how do we look at the rate equation in case we are given particular conditions. So if we consider the rate, let the rate equal to K, concentration of A to power 0, and obviously this would give us a rate equal to K, and that is zero order reactions. So for zero order reactions, rate will always be equivalent to K. Now, what other else do we need to also note? That rate, when we talk about the reactants, is also equal to negative the concentration of reactants divided by time, or the change in time. So if I consider this and that, then therefore I find that negative d concentration A divided by change in time will equal to K. So if I integrate, of course, I'm going to transfer this dt this side and then integrate. So negative A, then A, negative d concentration of A is equal to K dt. So I'm going to do integration, and I'll find that negative concentration here will equal to Kt plus a constant. Now let us consider conditions, okay? We are going to consider conditions where we are going to be integrating from 0 to a particular concentration T. So if we are integrating from 0 to T, then we will have that this will be negative A. So we are substituting in our limits 0 to A T, which is equal to, obviously, if we remove the constant and put the limits, then this is going to be from 0 to T. Yes. So now what is this going to be? This is obviously going to give us negative A, okay, negative A concentration T. This is equal to Kt. Okay, so remember we are saying this is that minus that, so obviously what is going to happen is going to be this with a negative, then obviously minus a 0. So what is that going to be? Obviously this is going to be remember we are, let's do it properly. Let's rub here. So we have minus, okay, minus 0. Okay, so we have to remember that initially the concentration is not going to be 0. So the initial concentration is going to be the concentration at t is equal to 0, so that we have plus, okay, minus, then minus the concentration at t is equal to 0, and this is going to give us Kt. Okay, then from there we'll have this, and we'll have the concentration at t is equal to 0 minus the concentration the concentration at any time t, this is equal to kT. Okay, so what is this going to give us? So this is going to give us, if we want, for example, this, of course, we want the concentration at any time t. This is equal to the concentration at time is equal to 0 minus kT. So this is for first order, zero order reaction, and this is obviously going to give you a graph that is like this. It is going to be starting from the concentration at t is equal to 0, and it's going to be going down with a gradient, and I mean a negative gradient. So that is going to be that. So we want to look at the half-life. Let's look at half-life for zero order. So for zero order reactions, we are going to put that at t is equal to t, okay, after t is equal to t a half, then we find that this concentration at that time, okay, will have become, that is after t is equal to a half, this will equal to the concentration divided by 2. So what we do, so ladies and gentlemen, if we are looking for the half-life, we are saying already after the time equivalent to half-life, the amount that is going to be present, of course, from the initial concentration is going to be half of the initial concentration. So what does that mean? We are saying after t a half, then the amount that is going to be. So that means we can say that if you are looking for the concentration at t a half, this is going to be the initial concentration at t is equal to 0, of course, divided by 2. So we're going to substitute in this equation so that it becomes, it's going to be a half, okay, of the initial concentration, equivalent to the initial concentration minus k times t a half. So when we transfer this here, you will have this a half of the initial minus the initial concentration equivalent to negative k t a half. So obviously this gives me negative initial concentration divided by 2 equivalent to negative k t a half. So this and that will go away, and what remains is going to be, this is going to be t a half equivalent to the initial concentration divided by 2 divided by k. So that's where this expression comes from, and we can use it to calculate for half-life in zero-order reactions. So let's look at the examples of zero-order reactions, and one of them is iodination of propanol. So iodination of propanol means that we are going to get propanol, CH3CO, CH3, which is in aqueous form. We are reacting it with iodine, which is also in aqueous form, to produce 1-iodopropan-2 on. So this is going to be CH3CO, CH2, and we are giving you iodine there, then plus we are adding plus hydrogen iodide. So then that is one example. Then the other one is the decomposition of hydrogen iodide on a gold surface. So you have the composition of hydrogen iodide. Okay, this is a gas, so it is going to give us hydrogen gas plus iodine gas, and then we shall put a 2 here to balance the chemical reaction. So this is in the presence of a gold surface. Then we have the composition of ammonia to nitrogen and hydrogen by hot tungsten. So this is also another example. So we have another example, the composition of ammonia. So you have NH3 gas giving you hydrogen gas plus nitrogen gas. So we shall just do a balancing. We put the 3 here. Remember, this is in the presence of hot tungsten as a catalyst. So these are the examples in which we have zero order reaction, and you can master them, and whenever a question comes, you should be able to answer that. So in this discussion, we have been able to give us, we have been able to discuss what half-life means, the concepts of half-life, why do we need it to, and what are the applications of half-life. We have discussed the equation for determining rate of the reaction, or the rate equation for zero order, and from which we derived the equation for determining the half-life of the zero order reaction. Then later on we gave the examples of zero order reactions.